Part A is testing your knowledge of the relationship between position, velocity, and acceleration. The derivative of position gives you velocity, and the derivative of velocity gives you acceleration. The acceleration is the derivative of velocity. So to find the acceleration at time 3, we can find the derivative of velocity at time 3. This is a calculator problem, so use your calculator to evaluate the velocity at time 3. The AP exam requires you to be accurate to 3 place values. The rounded value is negative 2.118. Part A was only worth 1 point. The point was awarded for the answer negative 2.118. In Part B, we're given a velocity function and a point on the position function, and we want a point on the position function. The integral from time A to B of velocity equals the change in position is the equation that involves these 3 items. The change in position is specifically the position at time B minus the position at time A. Here's the given velocity function, the known position, and the position we want. Substitute the velocity function. Zero is the given time of our known position, which will be our lower bound. 3 is the time that we want the position, which is our upper bound. The integral of velocity from time 0 to 3 is the change in position from 0 to 3. If we found the position at time 3 and subtracted the position at time 0, this is also known as the displacement over the time 0 to 3. Using your calculator to integrate the velocity function from 0 to 3, you get 3.2397868, which equals the position at time 3 minus the known position at time 0, which is negative 5. Simplifying the negative, it becomes positive. Now to get the position at time 3 alone, subtract 5 from both sides. The position at time 3 is negative 1.760. I rounded to 3 place values because the test requires us to be accurate to 3 place values. Part B was worth 3 points. The first point came from setting up the integral from 0 to 3 of v of t dt. The second point came from using the initial condition, which was the particle's position at time 0, which was negative 5. And the third point came from the final answer, negative 1.760. Part C is with calculator. So with your calculator, you integrate from 0 to 3.5 of the velocity function, which gives you 2.844 when you round to 3 place values. Next, we'll interpret the meaning of this integral. The most concise way to write the explanation is the displacement of the particle from time 0 to time 3.5. But let's talk about what displacement means. In Part B, we set up an equation where the integral of velocity equaled the change in position. Displacement is really change in position. In this case, the change in the particle's position from time 0 to 3.5 was right 2.844. Another way to say the same thing is if we measured the distance from where the particle was at time 0 to where the particle was at time 3.5, we would get 2.844. Positive 2.844 because the particle is to the right of where it was at time 0 at time 3.5. A visual explanation would be to graph the velocity function. The area in green represents the distance the particle traveled to the right, and the area in red represents the distance the particle traveled to the left. So at time 0, the particle began moving to the right. It stopped at time 2.8024956, turned around, and then backtracked to the left a distance equal to the area in red. At time 3.5, the particle ends up being to the right a distance of 2.844 of where it was at time 0. To evaluate this integral, you will need to use the absolute value feature on the integrand, in other words, what's between the integral and the dt. To do this on an Inspire, you can just use the button to the right of number 9 on your keypad. On a TI 83 or 84, the quickest way to get to absolute value is to just simply hit second 0, which gets you to the catalog, and ABS is the first one listed. The most concise way to interpret the meaning of this integral is to say the total distance traveled from time 0 to time 3.5. This ends up being the area of the green plus the area of the red, rather than subtracting out the area of the red. This is a good time to remind you of the difference between finding the integral of a function and the integral of the absolute value of a function by hand. You would start by finding any x-intercept located on the interval from the lower bound to the upper bound. Next, you would break up the integral from the lower bound to each x-intercept until you got to the upper bound. After breaking up the integral by its x-intercepts, you would take the absolute value of each integral. The first integral here, from 0 to 2.8024956, would give you the distance traveled to the right, so you'd get a positive answer. And the second integral, from 2.82496 to 3.5, would give you a negative answer because it's the distance traveled to the left. Absolute valuing each of them, we would then add them together and get the total distance traveled. In part D, let's start with notation. For the first particle, x of t represents position, v of t velocity, and a of t acceleration. For the second particle, we use a subnumber 2 to represent the position, velocity, and acceleration for particle 2. To find the time when the two particles are moving with the same velocity, we need to set the velocities of the two particles equal to one another. We were given the velocity function of the first particle, but need to find the velocity of the second particle. The derivative of position gives us velocity. The derivative of velocity gives us acceleration. The derivative of the second particle's position function is its velocity. So the velocity is 2t minus 1. Now we can set the velocity of particle 1 equal to the velocity of particle 2. Using our graphing calculator in radian mode, graph the left side and right side. The solution to this equation is located at the intersection of the two curves. We're only looking between 0 and 3.5. Using the intersection feature, we find t is equal to 1.571 when we are accurate to 3 place values. So the two particles are moving at the same velocity at time 1.571. Part D was worth 2 points. The first point was for setting the velocities of the two functions equal to one another, and the second point was for the answer 1.571.